Assalamu alaikum. Hello guys. So sorry for inconvenience yesterday. I didn't give you a proper lecture, so I'm again recording the previous lecture. So before starting the problems, I want to give some clue about the continuity equation and the energy equation. For example, we have a node or a junction where four pipes are connected at the junction. For example, junction of A and the pipe are connected of number 1, 2, 3. So one point to remember that we have to satisfy the continuity equation at junction. Continuity equation at junction and we will satisfy energy equation for pipes. So we know that for continuity equation, the we first have to assume the direction of flow. So for this scenario, we are assuming that the flow is flowing in this direction and outflowing from the junction in this direction. So according to the direction, we have to satisfy the continuity equation. So at junction A, the continuity equation will be written such as Q1 plus Q2. I'm taking a positive sign because at junction A, the flow from pipe 1 and 2 acting as a inflow at junction A, while for 3 and 4, it is acting as a outflow. So it is an explicit function. To solve it easily, we have to make an implicit equation by keeping these closed equation at one side to solve it easily. So for continuity equation for any junction, we have to satisfy such type of condition. While for energy equation, we have to satisfy the Bernoulli equation. Just for the case of pipe A, we assume that it is a point B and the flow is flowing from B to A. So this point will have some elevation from a datum. For example, if I consider a reservoir at this point, so at reservoir, as we know that the pressure is atmospheric, therefore the pressure at the water level will be zero and also the velocity will be zero. So for the reservoir case, we will consider only the elevation head. While at a junction, we have a combination of the elevation head plus the pressure head plus the velocity head. So the total head at reservoir is equal to the elevation head, while the total head at a junction A will be equal to the summation of the elevation head, the pressure plus the pressure head plus the velocity head. So okay, to satisfy the energy equation for a pipe, so it is necessary to assume a direction to know about the direction of a flow. So the water is flowing from B to A. Therefore, the energy equation for the pipe A will be such that the head at B minus the head at A minus the head loss is occurring through the pipe is equal to 0. The energy equation basically be written as HB, the head at upstream, is equal to the head at downstream plus the HL But this explicit equation, we have to make it implicit to solve it easily just by keeping it one side. So now let's solve the problem. So to solve a problem, to solve this problem, so the so we know that we are given a three reservoir having the elevation head of each reservoir. For a B, it is about 120 feet. For A, it is about 110 feet, and for a C, it is about 70 feet. And the perimeters of each pipe is also provided to us. So to solve this problem, and the requirement of this question is to calculate the pressure head or the pressure at point D, and the elevation and the elevation is given to us. So based on the required information, the given information, we will calculate the pressure at D. So we have a three-user wire. First, we have to assume the direction of the flow. So we are assuming that the flow is flowing from the B to D and from A to D and from D to C. So we have to denote each pipe. So the pipe, this pipe will be denoted as AD. This pipe will be denoted as BD, and this pipe will be denoted as DC. So each pipe have specific material, cast iron, galvanized iron pipes are we are using for this problem, and each pipe also have a roughness coefficient. So based on the material, we will get the value from this absolute roughness table. So for a cast iron, it is about 0.00085, while for the galvanized iron, it is about 0.0005. So the lengths are also given, the diameter are also given. So based on the diameter, we will calculate the area. So to solve the pressure at this point, first we have to assume, because we don't know about the height, pressure head, anything else except the elevation head. So if you don't know about the pressure head and to find a pressure head, so in such a problem, we first have to assume the pressure head or the pressure at the required point. So I'm assuming a pressure head of about 109.6. So based on this pressure head, I will calculate the losses occurring at D, BD, and DC, because the based on the pressure we can see that the pressure head will be less than as compared to the head at each reservoir of reservoir B and A. Because when the water flows through pipe, so there is always a pipe friction. So due to that friction, the losses occurs. So the losses will be the losses at D from the losses of a pipe AD will be the 110 minus the head assumed at this point. Similarly, for the pipe D, the losses will be the head the head at point B, the water level at point B minus the head at D, and so the flow is flowing from D to A. Therefore, the head at D will be the head at D minus the head at C. So we also don't know about the fraction. So so we first have to assume the fraction factor. Okay, so based on this fraction factor, we will use the Darcy-Weisbach equation to calculate the velocity based on this fraction factor. So we know about the head loss, the diameter, the G, and the L, and we have assumed the F, and also the HF is calculated based on the assumed values. So first we will calculate the assumed velocity based on the assumed values, Then we will calculate the assumed Reynolds number based on the assumed velocity, because velocity is also calculated based on the assumed values. So based on these assumed values, we will again calculate the fraction factor. So Reynolds number will be calculated by VD by nu. VD is the velocity 27 is the cell reference is velocity, uh, and d into d divided by the kinematic viscosity. So we are taking the kinematic viscosity for this system, for the water flowing the system, about 0.00000113. So based on the kinematic viscosity, velocity, and the diameter of a pipe, we will calculate the Reynolds number, and again we will calculate the fraction factor based on the Jane equation. This equation using this equation by using the absolute roughness, the diameter of a pipe, and the assumed Reynolds number. So after calculating the fraction factor, we will again calculate the velocity, and then we will calculate the flowing through each pipe. So as we know that at junction T, the flow from BD and AD are acting as a inflow, while for DC it is acting as a outflow. So therefore we are uh, mentioning the direction of each pipe, that how it is flowing through each pipe. So based on the direction of a flow, we will calculate the flow in each pipe. Q is equal to AB, just by multiplying the velocity with the area, and then we will calculate the outflow equal to the inflow, and then satisfy the continuity equation at D to make it this number to zero. Then we will get the required pressure head at D. So just copying and pasting. Okay. So we first to solve the first equation, we assume the fraction factor. So based on this fraction factor, we again calculated the fraction factor. So we will use the new fraction factor that we calculated in the previous iteration, equal to this fraction factor. So the outflow, when outflow minus inflow is greater than 90, so it means that we are assuming a value higher than the actual value. So we have to reduce the 109.65 to the 109.15. So the value little bit decreases. So again, third iteration. So basically, so we will use the fraction factor value of the previous iteration to again calculate the outflow and inflow through D through junction D. So the value is merging to the zero. So we will little bit arrange it again to 4 5, because the value is greater than the outflow minus inflow is greater than zero. So we have to reduce the pressure head at D. So it is little bit equal to the zero. So the minus means that we are assuming the pressure head at D less than the actual value. So make it 7. It will be equal to approximately equal to 0. So automatically, to calculate it automatically, you can do it by goal seek. So goal seek is a tool in Excel. We can easily calculate the iterative problems. So I am keeping the set cell. The objective of my cell is to keep this value to 0 by changing this value. So it will automatically change the value of pressure head, and we will get the required answer. Right? the required objective and the cell we have given a reference to the policy. So it gives us the pressure head of the bound 1.145. So this is our required pressure head LD. So based on the pressure head LD, we have to calculate the uh, pressure at D. So we know the elevation head of point D. So before calculating the pressure at D, we have we will also calculate the velocity at each pipe and take the average of this velocity head moving the water flowing through each pipe. So it have some velocity. So we will take the average of this velocity. So 1.26 basically the average velocity head by taking the average of these three values. So we have the velocity head, similarly the elevation head are given to us. It is about 85, and the AG we have calculated by guessing or by the problem as we solved uh, earlier. So based on this equation, we will calculate the pressure at D. So HD minus elevation head minus the velocity head multiplying the unit weight of water in FPS system. In FPS system, it is about 62.4 pound per foot cube, and SI system it is about 9.81 Newton per meter cube, and then divided by 144 to convert it into PSI. So if you want to increase this value, if you require that the pressure at D should be 14 psi according to the standard, then you have to minimize the losses occurring through the pipes and the water flowing through it. So I will increase the diameter of this pipe, and will do again the iteration zero by changing this value. So it little bit increase the value increases little bit. Now so we can examine that by increasing the diameter of this pipe does not affect greatly the system. So we will change the diameter of this pipe. So increasing the diameter of now again solve the problem. So we think we are assuming the wrong value. Let's signal 1.5. Okay, I got the point because we cannot get the head greater than the 120 because the elevation head of a reservoir is about 120. So the head at this point will be approximately is about 110. It cannot be greater than 110. So the maximum head we can achieve is about 10 head, 10 meter, 10 psi at point D or the head of 109 or about 110 feet at point D. To increase the head, we have to increase the head at B. So you can do this by iteratively and increase the pressure head at point D. Now solve the now again solve the two reservoir problem. So I will go through it. It's a bit costly. So the perimeters of each pipe are given to us. The perimeter of each pipe are given to us. The length and the length, diameter, and the Hayes and Williams coefficient. So based on these values, we will calculate the pipe constant, and based on the pipe constant, we will calculate the head losses occurred through each pipe. So the pipe constant will be calculated based on the this Hayes and Williams equation, and the head loss will be calculated using this equation. So I just apply the condition that I have resumed the flow through each file. So I just to know about the I want to know about the am I assuming the right direction, therefore applying this condition, so I will to find the actual flow direction in each file. And other point is that when we applied the coefficient or exponent of 1.852, it did not it doesn't give us a proper value for each equation. It gives us a different value. Therefore applying the condition by applying the absolute function as well. So the elevation head of each junction are also given to us. We have also given that the demand at each point. So the demand may be the residential, commercial, the demand, the budget of mass, so anything connected to point depend on that the demand. So the demand will be the having some value. So these are the considered it is summarized or the total value, the total demand at each junction. So we also don't know about the head at one because we don't know about the flow at each pipe. So we will assume the flow at each pipe and the head at each junction. So to satisfy the energy equation, let's go to the part A. So it will be equal to the head at A minus the head at B by the minus the losses occurring to pipe. But first, remember that you have to assume a direction of flow. If you don't know about the direction, then you can quantify the energy equation or the continuity equation at each junction or at each pipe. So similarly for pipe 2, it will be equal to the head at 2 minus the head at 1 minus the head losses occurring at pipe 2. Similarly, the for pipe 3, the head at 3 minus the head at 2 minus the head losses occurring through pipe 3. Similarly, for the pipe 4, the head at B minus the head at 3 minus the head losses occurring to pipe 4. While for the continuity equation, the inflow taken is positive while outflow is taken as negative. So the demand is also negative, and for the pipe flowing, outflow for the pipe flow through the from junction 1 is also negative. So the equation will be the head junction will be the Q1 plus Q2 minus Q6 minus D. So I have written all these equations. You can observe these equation. I just applied here to solve this equation. So this is basically make it I write it here to solve it easily through solver. So I will apply a solver and that. So these are the constraint I applied here, that the energy equation for each pipe should be 0 and the continuity equation at each junction should be 0. So you can apply it by using uh, just again this it all. I will apply for each pipe. and for each junction. So I am going to reference each cell and make it constant to 0. So solver and goal seekers are very just tool in itself to solve iterative problems. You can do that also as VBA, but it is very difficult and time consuming to learn about that. But the programming tool and it's best if you have time to learn about that as well. So we have given a constraint to the solver that these cells should be equal to 0 by changing the values of these flows and head values by solving these equations. So to before solving, you should make this make unconstrained variable non-negative. So it will solve properly then. Okay. So the solver has solved for us the problem. So the negative sign shows that the direction we have assumed were wrong. So the negative direction shows that the flow in each pipe that the direction we have assumed were wrong. So in a pipe 2 we assume the direction from 2 to 1. So in actual it is flowing from 1 to 2 and similarly. So the red direction shows that the assumed direction were wrong where we assumed the previous iteration. So that's all about this lecture, these problems. So if you have any questions you can ask. So please watch these videos before the next class so you're able to ask question in that class. Thank you. Assalamu alaikum.